Professor B R Mehta, his specialization is experimental solid-state physics and material science, nanoscience and technology. His areas of interest are nanostructured materials and thin films, interaction of gas molecules with nanoparticles, nanoparticle-based gas sensors and switchable devices, rare earth metals and palladium nanoparticle structures, wide bandgap and bipolar conductivity oxides, scanning probe microscopy and high resolution microscopy and nanotechnology education. His areas of research are synthesis of nanoparticles and nanorods, structures for sensors, switchable mirrors, light emitting and photovoltaic applications. Let us invite Professor B R Mehta to give his lecture on nanoscale switchability, nanoscale switchable mirror, sensor, resistive memory and solar cell devices.
My lecture is basically on devices, different types of devices in which nanoscale quantum effects and other effects have been utilized to improve the properties and characteristics of these devices. And possibly maybe in future these devices will be used for some sort of a nanocomputing or other kind of application. So as already mentioned, the title of my talk is Nanoscale Switchable Mirror, Sensor, Resistive Memory and Solar Cell Devices. And my main objective has been to give you an idea about what kind of research I am involved at IIT Delhi. And these are in fact 3 or 4 areas of research in which I work. And what I am going to show you in this talk is that in all these 4 kind of devices, we have been able to use one or the other effect which arises because of nano dimension. So I will be taking in this talk, I will divide it into 4 talks. And the first example which I will discuss is rare earth based nanoparticle based switchable mirror. And I will show you that in this the effects due to size, the change in the properties of this rare earth materials due to small nano size and increase in surface area at small sizes has been utilized to improve the performance of the switchable mirror device. In the second example, which is a hydrogen sensor based on palladium nanoparticles, not only the size effects but also certain very interesting effects which arises due to the gap between the nanoparticles. So we not only one has to control the nanoparticle size for improving the properties, in some application it is also important to position the nanoparticles so that you can control the gap between the 2 nanoparticles. And in this case I will show you the interesting effects which arises that there is a certain gap between the nanoparticles in the nanoparticle sensor. Third device I will talk about is nanorod based resistive memory device. And these nanorods we work on based on some oxide material like copper oxide or nickel oxide. And this resistive memory device we have been able to normally conventional resistive memory devices are based on thin films of oxide materials. And by changing the thin film to a parallel network of nanorods, we have been able to show that the performance, the uniformity, the cell-to-cell uniformity of the device can be significantly improved. And this effect is due to the confinement of certain effects which takes place in thin films to the nanorod dimension. And I will try to describe that. And the fourth effect, I think, is very popular devices, solar cells, which has very much useful for especially energy applications. And here, by controlling the size, you can change the various properties, and that change in the properties can be utilized in improving the efficiency of solar cell devices. So my basic idea is by controlling the dimensions, by controlling the diameter of the nanorod, controlling the length of the nanorod, by controlling the gap between the nanoparticles, how we can improve the performance of the device. And because all along the properties and other characteristics of these materials and devices depend upon the dimensions. It is very important to control the dimensions when one is synthesizing the nanomaterial, because this is one of the biggest challenge before the material scientists when they're growing these nanoparticles and nanorods. How do you control the nanoparticle size, and how do you control the nanoparticle distribution in size, how do you control gaps, and so on. And this is also one of the feature I will try to describe, that how we have developed a certain synthesis route where it is possible to prepare what we call as some sort of a mono-sized nanoparticles which don't have much distribution or very small distribution, or we can control the distribution, I would say. So this is the first example I was mentioning, nanoparticle, rare earth nanoparticles based visual mirror. I will spend around 10 minutes on this, and this is just an introduction. What is a switchware mirror? And switchware mirror is normally conventional switchware mirrors are based on thin films or bulk rare earth materials. And these rare earth materials have interesting properties that when they interact with hydrogen, they react with hydrogen, there is a change in the electronic and optical properties of the rare earth material on interaction with hydrogen. And this is what happens. So when you have a conventional rare earth material, and normally in most of the switchware mirror devices, it is covered with a palladium overlay, which I will describe you what is the need of palladium. And when we put hydrogen, it goes from metallic state, which is, in this case we have taken the example of gadolinium, it goes to gadolinium dihydride. And when you put more hydrogen, it goes to a trihydride. And if you remove this material from hydrogen, it will come back to dihydride state. And thus from dihydride to trihydride, one can go back and forth. And when one is doing that, what is there is there are three transformations taking place. One, there is a crystal structure transformation. Gadolinium dihydride has FCC structure, whereas trihydride has a FCC structure. So there is a crystal structure transformation. There is a metal to semiconductor transformation, and there is an optical transformation. In the metallic state, it's a reflecting. Gadolinium dihydride is dark color in reflection mode, and trihydride is transparent color in the yellow color in the transparent mode, because it's a semiconductor. And what is interesting is that this transformation, two transformations, metal to insulator and the crystal structure transformations are taking place at room temperature. From solid state physics point of view or chemistry, it's very interesting that it's possible to put 300% of one material into another. Hydrogen, 300% of hydrogen we are putting when we go from gadolinium to gadolinium trihydride, and you can remove 1/3 of it reversibly, room temperature, and this is what is very interesting from physics point of view. Another very interesting effect is that these two transformations, which I was mentioning, structural and electronic transformations, are independent to each other. The metal to semiconductor transformation is not taking place due to structural transformation, because there are many other rare earth materials. In gadolinium, there is a structural transformation. There is another material like praseodymium. There is no structural transformation, but there is a metal to semiconductor transformation. So the reason for these two types of transformations are totally different. And this change in the optical and electronic properties, because you can change from a mirror-like state to a transparent state, is what is called a hydrogen-induced switchware mirror. You can use the change in electrical properties, or you can use the change in optical properties. Why palladium is required? Because it's not the molecule of hydrogen which interacts with the rare earth material, it is the atomic hydrogen which interacts and reacts with the material as we go in this direction or when we come back in this direction. So what the role of palladium is that palladium converts the molecule of hydrogen into atomic hydrogen. Both when hydrogen is going in, when we are going in this direction, and also when the hydrogen is coming out, when we are coming back in the reverse direction. So this is called dissociative absorption. Molecule of hydrogen gets absorbed, gets converted to atomic hydrogen, and atomic hydrogen gets with the rare earth material. When the hydrogen has to come out, two atoms of hydrogen has to come together at palladium site, form hydrogen molecule, and the hydrogen molecule comes out. It's slightly complicated. And also, palladium protects the rare earth material from oxidation, because rare earth material gets converted to oxide very easily. And this is how you can see that when we put hydrogen, there is a large change in the optical properties, resistivity and transmission. Here is metallic, transmission is very low, the transmission is very high. So this change in the optical transmission from this point to this point, or change in the electrical properties from this point to this point, is what is used as in large number of these applications. One of them which we studied is switcher mirror. And what is required for a good switcher mirror is color neutral transparent state. In the transparent mode, you don't want the transparent to have a color, like gadolinium trihydride has yellow color in the transparent mode, and reflection it has a blue color. In the transparent mode, you want it to be color neutral, so that the transmission is same at different wavelengths of light. Color neutrality, response time, optical contrast should be large, stability towards oxidation, and reproducibility and reversibility. These are some of the parameters. And large number of systems people have tried, which improves one parameter and deteriorates the other parameter. And when we started this work something like 5 to 6 years back, our idea was to use nanoparticles, two effects, blue shift due to quantum confinement effect. When the electrons are confined to smaller dimensions, there is a change in their electronic state and there is a change in their properties. For example, one of the properties which we discuss with students especially which is very interesting for physics students, is the change in the band gap of a semiconductor by controlling. As you reduce the size, there is a blue shift in the band gap of semiconductor at smaller size. And the shift depends on the projection size. As you go to smaller and smaller, the shift increases. So we thought that by not by changing, like in these examples that people did, they put some other materials into it, and we changed the interaction of rare earth materials with hydrogen. We thought we will just make the rare earth materials in nanoparticle form and shift the band gap of gadolinium trihydride from yellow to ultraviolet, and so that it becomes color neutral. And also the second effect of enhanced surface area, the passive surface area of nanoparticles, surface area per unit volume increases as we go to smaller size. And hence it is expected that the interaction of nanoparticles with gases will increase, especially with hydrogen. So this was another idea. So because of these two effects, we thought we were able to make rare earth nanoparticles, which is very difficult to form because of the third reason. They form oxide. Most of the chemical methods cannot be used for making nanoparticles of rare earth materials. So we started working on this. So another effect which takes place when we go to smaller size is a change in the crystal structure. And whenever there is a change in the crystal structure, it is also expected that it will affect the interaction of hydrogen with the material. So we are not sure how this change in the crystal structure due to size will affect the rare earth hydride interaction, but we are very much convinced that the blue shift due to quantum confinement effect and enhanced surface area will improve all the parameters. And when we started working on this, there are 3 or 4 systems that we worked. I will describe very briefly. The first system was that we make nanoparticles of one rare earth and we covered it with a palladium overlay, like in conventional devices. And what we observed is that all the properties which I mentioned with the requirement for a good switcher mirror, the color neutral state improves due to the blue shift in the band gap. Increase in the optical and electrical contrast because of enhanced surface area, and there is a reduced hysteresis when you're putting hydrogen and when you're removing hydrogen. The change in the electrical and optical properties do not follow the same line in conventional devices. And what we found is that in case of nanoparticle devices, the hysteresis is very less, and this is due to the structure changes and the slag topography, which I will discuss later. Slag topography means in conventional to thin films, which have a very complex structure, nanoparticles have voids in between them. So they provide space for the material to expand and contract when we are putting 300% of hydrogen, and this reduces the hysteresis which is absorbed. So this was a very tremendous effect that just by going from a thin film to nanoparticles, all the properties of the material of the device improve. This was a very simple change and very large effect. As I already mentioned, the rare earth materials are susceptible to oxidation. So they react with oxygen very quickly at room temperature. And when you make nanoparticles, you expect your nanoparticles will interact with hydrogen more. But they will also interact with oxygen more because they have a large surface area. So we wanted to investigate what is the effect of going from bulk or thin films to nanoparticles on their reactivity or stability in oxidation. And we were surprised to know that these nanoparticles we found are stable in air. And that's what takes place due to the cell structure. The oxide around the nanoparticles protect it from further oxidation. In normal conventional bulk or thin film, this oxide is not protective. The oxide, because it has a different crystal structure from the metal, it comes off and it exposes the other material to oxidation. This causes splitting. In case of nanoparticles, because of structural changes which has taken place, the oxide becomes a protective oxide and it protects it from oxidation, but it is so thin that the hydrogen can go in and come out. So this was a very interesting effect, and it was possible to hydrogenate it, put hydrogen into the rare earth material and take it out without the requirement of radium, and that is some sort of a surface activation is responsible. The presence of surface sites which convert molecule of hydrogen into atomic hydrogen and hence do not require radium. The third effect we investigated by changing the top layer of radium to thin film to nanoparticles. So the hydrogen comes, it reacts with these nanoparticles, gets converted to atomic hydrogen, and that is what goes inside. And what we observed is a fast recovery and so on. I will discuss this particular effect I will discuss later. What I want to show you now is that in this transparency I have shown that these are nanoparticles prepared by a very simple method, but there is one problem as I shown here, these particles are of different sizes. Because you don't have a control on the distribution, this is very important. Although I can say that this large improvement in the properties of the material, going from bulk to nanocrystalline or nanoparticle form, I cannot say what happens when they change the size because I don't have a size control. The size distribution of these nanoparticles is very broad. And this is one of the limitations when you have a synthesis method where you don't have a very good control of the nanoparticles. So what is important here is the lesson that we must have synthesis method in which we must be able to control the nanoparticles. So these are our initial results, and then we started working on a synthesis method where it should be possible to control nanoparticle size and their shape and the size distribution. So this we call is some sort of a integrated. This is the integrated deposition method, consists of 4 and 5 steps. The first step is just a very simple method of converting the bulk material into atoms of the material. It's like evaporating the material. We found a different method, but what we are doing is a spark generator. 2 rods of, let's say we are making palladium nanoparticles, we have 2 rods of palladium, there is an arc between them, and because of that the palladium goes to the vapor phase and the carrier gas A and B takes these vapors along this line. And as they are going, these atoms collide with each other and they form agglomerates. And as shown here, these agglomerates are of different sizes. They are having arbitrary shape because they are formed due to statistical mechanism of collision of these atoms, and then they form small particles. These small particles will again collide and form agglomerates. And what we do is we take these agglomerates to what is called a UV charger, where the UV light falls on them and these agglomerates are charged positively and negatively. These positively and negatively charged particles, agglomerates, goes through another machine which is called differential mobility analyzer. The gas takes these agglomerates into this device, and the device consists of 2 cylinders, and there is an electric field applied between them, and because of that there is electrical force in the radial direction. The gas takes the particles along the longitudinal direction, and particles having a particular velocity will reach the exit point, and hence depending upon what is the electric field between the inner electrode and the outer electrode, you can select particles of a particular mobility. Particles having a particular velocity in the gas is proportional to the size of the particle. But you can say that still they are not having the same shape. Then the particles are taken to a sinking furnace, the gas takes them, there is no substrate effect, and the particles are still floating in the gas. They form spherical droplets, and slowly when they come out, They are monocrystalline and spherical in shape, and they have the same size because of the differential mobility analysis. What is important here is that you can see these particles are positively charged particles because the central electrode was given the negative voltage. If you give the central electrode positive voltage, you can select negatively charged particles. This is important as I will show you later. So these particles are still charged here, and these spherical monocrystalline particles having the same size are deposited onto the substrate, and then it can be. So now we can change the size of these nanoparticles by applying the electric field. We can control the size distribution of these nanoparticles. You can see that if we didn't do any selection, this is the size distribution we would have. This is the size distribution of those agglomerates. And once the selection has been taken, this is what we have selected. Although we have thrown large number of particles out, the yield of this process will not be very good, but for electronic application, where you require a very good control of the nanoparticle size, this is a very good method. And it works very nicely for rare earth materials and for palladium. So we have deposited nanoparticles of palladium, osmium, deuterium, gadolinium by this method. And this is the deposition method consisting of, and this is the nanoparticle spark generator and UV charger, DME, this is the sintering furnace, and the fine UV particle and deposited. This is what you can see, that these are those agglomerates having different size and shape, and as they go through the sintering furnace, depending on the temperature, each agglomerate, if they lose agglomerate, it will get converted to this spherical particle. Okay. And you can see that by giving the different voltage to the differential mobility analyzer, you can select particles of different size. The size distribution is very symmetric, standard deviation is less than 1.05, and you can see that if you see this one of these nanoparticles in the high resolution transmission electron microscope picture, it is almost monocrystalline. So different experiments can be done, and this is what if you look at, this is now a palladium nanoparticle layer deposited on the glass on a particular substrate. This is what we are looking at, is the cross section of this by using a ion milling technique, where some sort of these particles have got distorted because of the effect of the ion beam, but still you can see one of the important features here, what I am trying to show is there are gaps between the nanoparticles. You can see there are voids, and these voids change the interaction. One of the reasons why the interaction of hydrogen with rare earth nanoparticles and palladium nanoparticles get affected is that the presence of void plays a very important role. So one of the reasons is the flat topography, the presence of the voids, interparticle gaps. The second effect is that when we decrease the size of the palladium, when we go from around 10 film or around 30 nanometers to 5 nanometers, there is a shift in the electronic state of palladium. And one of the important states of palladium which is responsible for its interaction with hydrogen is palladium 40. It is in fact palladium 40 electron which interacts with hydrogen 1s state. Larger is this overlap, larger is the interaction. This is called a D-band model, and what we observed is when we change the size of the palladium from 30 nanometers to around 5 nanometers, there is a shift of the palladium 40 centride away from the Fermi energy, which is responsible for increased interaction of palladium with hydrogen. And this is one of the reasons. Presence of voids, increased interaction of palladium with hydrogen, and the other effect which we see is that there are two other things which are taking place when hydrogen is going into palladium. And one of them is that hydrogen acts like scattering centers for electrons. So when hydrogen will go into palladium, it will increase the electrical resistivity of palladium because mobility will be affected because of the scattering process. And so there is a 10 to 15% decrease in the electronic mobility, and the other effect which takes place is that the change in the lattice parameters. The expansion of the material takes place. So you go from this is the palladium lattice constant. As you start putting hydrogen, low concentration of hydrogen, you have the alpha phase. Then the concentration of hydrogen increases, you have a beta phase of hydrogen. So when you go from alpha phase to beta phase, there is some sort of a 4% expansion in the lattice phase. And that is the reason that you require that void. If the void is not present, if the topography is very compact, the nanoparticles palladium cannot expand, hydrogen cannot go inside, and it cannot come out also the same way. So what we observed is that in case of nanoparticles, because of the presence of these defects or the presence of these gaps, if we do EC2 X-ray diffraction which tells us the structure, in case of thin films, we can say that even up to 10% hydrogen, up to 2% hydrogen or 5% hydrogen, you can still see the alpha phase of radium. Not much hydrogen is going in. You have low concentration phase alpha and also high concentration phase of beta. But in case of nanoparticles, even at 2%, we have only beta phase. So because of all the effects which I discussed, more hydrogen can go into the palladium, even at smaller concentrations of hydrogen. So these are the four effects which I have discussed, and this effect we could see the effect of these 4 or 5 parameters on the sensor characteristics of palladium. So your palladium thin film or palladium bulk, what happens is that if this is the electrical resistance of palladium, when you expose it to hydrogen, the electrical resistance of palladium increases slowly. At this point, you remove hydrogen and the electrical resistance goes back. This is called a slow saturation response. Most of the sensors which work for different gases, they have this kind of response. This is a conventional or a typical sensor response, which is called a slow saturation response. And you can see here, you put the hydrogen both, and this is how you will be able to detect the gas. What we observed is that in case of nanoparticles, you can see that by going from thin films to nanoparticles, the sensing response has totally changed. In place of the slow saturation effect, what we have is the moment we put hydrogen at this point, the electrical resistance goes up, it comes down by itself. Still the material is, or still the sensor is exposed to hydrogen. At this point, we remove the hydrogen off, the resistance goes up and it comes back to the same point. So in place of, you can see that here the resistance was just increasing and saturating. In the second case, the resistance goes up and comes down. This is called a pulse-like response. And what we now understand is that this is happening due to 2 reasons. One, the first effect, when the hydrogen starts flowing in, there is a change in hydrogen acts like those impurity atoms, acts like scattering centers for electrons. There is an increase in the electrical resistance. But when more hydrogen goes, palladium nanoparticles expand, there is a gap between the 2 palladium nanoparticles, they start touching each other. Because of that, the electrical resistance comes down. So initially the electrical resistance goes up because of the electronic effect, then the electrical resistance comes back because of the geometrical effect, because of the expansion of the lattice due to hydrogen. And same thing happens when you move it from hydrogen. So there is a large change in the response characteristic of sensors because of going from thin films to nanoparticles. And what we now know is that we can in fact mathematically separate. This is the pulse response, which I showed. This is actually due to this electronic effect and due to the geometric effect. And we can separate the two, and we can separate their sensitivity, that is a percentage change, and also the response time as a function of nanoparticle size, because we now have a very good control on the size of the nanoparticle, and we can understand this process as a function of nanoparticle size. What we understand is that as we decrease the size, the geometric effect, its sensitivity decreases, shown by this blue curve. And the response time also, it becomes, for the geometric effect, the sensitivity, the geometric sensitivity to the geometric effect decreases as we go to smaller size, and the sensitivity due to electronic effect improves as we go to smaller size. This can be explained. And same, so the electronic effect has a very faster response, geometric effect has a high sensitivity as we go to smaller size. And what we see is, this is shown here. So this sensor, which is based on palladium nanoparticles, you can also not only sense the gas, you can also measure the concentration of the gas. Because the concentration at which the sensor changes its response from slow saturation to pulse-like response depends on the temperature at which the sensor is operating, and also, so if the sensor is operating at, let's say, 40 degrees centigrade, the transition from saturation response to pulse response, it will take place at around 4%. If you operate the sensor at 80 degrees centigrade, that change will take place at around 8%. So this sensor is has interesting characteristic. It has a very fast response due to the electronic effect. It has high sensitivity due to the geometric effect, and it is concentration specific response. Depending on the concentration, it will give a slow saturation response or a pulse response. This one. Now I will go to the. So in fact, this is from by understanding the current transport mechanism of these nanoparticles, you could really confirm that the effect is due to the presence of these gaps between the particles. Without hydrogen, the carriers have to cross these barriers from one nanoparticle to another nanoparticle. When you put hydrogen, these nanoparticles expand in their volumes, these particles start touching each other, and the barriers are diminished or reduced, and the carriers it becomes more of a metallic type of conduction. So when we have nanoparticles, or when you have thin film pulse, the change in the electrical properties as a function of temperature is different. This is another extension of this work. Which I mentioned that depending upon the central voltage which we give to the central electrode, the particles can be positive. If you give the negative, if you give this positive voltage to the central electrode, you will have negative particles. So this is the work which we are doing at present. What we are doing is we have two lines for making these particles. In one line, we make particles of material A, which has positive charge of a particular size, and in another line, we make nanoparticles which are negatively charged of material B, having a different sign, and then we put them together in one coagulation tube, where these particles collide with each other and form pair particles, and these pair particles have various one of very interesting applications that we are thinking that one particle pair can form the spherical mirror which I was mentioning. With the palladium, it interacts with the hydrogen molecule, converts hydrogen molecule to atomic hydrogen. This atomic hydrogen interacts with the other particles, changes electrical properties, and using a connecting atomic force microscopy, you can see the change in the electrical properties of this nanoparticle. So this is some sort of research which we are doing at present. So this is the third device which I wanted to show you. This is called resistive random access memory devices. This is one of the potential candidates for replacing the flash memory which we use in these days. And one of the advantages of this device is that it has a very simple structure. The structure consists of a metal, insulator metal. So you have a metallic electrode, you have a thin film of that oxide material, the copper oxide, and you have a second metal. And when you apply a voltage between these two metals, there are certain changes, electronic changes which takes place in the insulating material, which can be used to define state 0 and state 1. So the advantages are low operating power, very fast speed, low cost, and a simple structure. This is how the device works. First, the device has to be, forming of the device has to be. That MIM structure has to be converted to a resistive memory device. This is called a electroforming step. When you do electroforming step, you apply a certain voltage, you can see that the current suddenly increases. There are certain electronic changes that are taking place in the material. And now the device is ready to use. So when you come back to this and you increase the voltage, the device after the electroforming step is in this mode. You call it low resistance state, or you can call it state 1. On application of the voltage equal to this reset point voltage, the device goes from state 1 to state 0. Its resistance increases again. When you apply the reset voltage, the device again goes back to the low resistance state. So by applying the reset voltage and the set voltage, you can change the state of this device from low resistance state to high resistance state and back and forth. So this is a simple idea of how this kind of devices can be worked as resistive random access memory devices. And there are two kinds of characteristics one normally gets. One of the characteristics is called unipolar, where the changeover from state 1 to state 0 only depends upon the voltage of the polarity has no role to play. In bipolar devices, the From state 0 to state 1 you go by application of positive voltage, and state 1 to state 0 you go by application of a negative voltage. Polarity is important here. So there are unipolar and bipolar switchable devices, and what we worked on synthesis of copper oxide nanoparticles by very simple method which is called template assist deposition, where you deposit these oxide materials into the templates of alumina, and then you remove the alumina and you have these standing nanorods which are fixed onto a substrate. And what this shows is this is one of the, you take one of these nanorods and see it in the high resolution transmission microscopy, see it in one signature schema. And this is how the actual characteristics of the device. This is the forming on application of around 11 volts, the device goes to a electroform state, and then the IV characteristics are this. On application of this voltage, you go to the set state and you can go back and forth. What is important is the on and off current ratio. The ratio of the current in this state and this state is something like 10 to the power 4, which is very high. This is one of the advantages of this kind of device, that the difference between the on state and off state in terms of the current or in terms of the resistance is very high. And then we look at the compositional changes within one nanorod. So you can see that this is the diameter of the nanorod, which was around 100 nanometers. This is the blue dot shows you the composition of copper and oxygen without electroforming, and the red dots are the composition after electroforming has taken place. And what we see is that after electroforming, there are certain points along the diameter where the composition has got changed. And what we understand now is that this has taken place due to the formation of some sort of a copper filament into copper oxide, or a metallic filament into the oxide. So it's like a small fuse between this metal and this metal which has formed due to electroforming. When you apply the reset voltage, there is a small rupture of this filament and the device resistance goes back to the high resistance state. When you apply the reset voltage again, the filament forms again and you go to the set voltage. So the device is going from the high resistance state to the low resistance state by the formation of these small filaments in the copper oxide. And this is a conducting atomic force microscopy picture of this nanorod sample. This is before electroforming, you don't see any variation in the current. This is after electroforming. You can see that individual nanorods, some of them show now low resistance state, and you observe high current in the conducting atomic force microscope. Again indicates that the effect is coming due to the formation of filaments into individual nanorods. So individual nanorod is acting like one particular resistive memory device. And our idea is that this is how it happens in conventional oxide, conventional thin film material. You have the filaments are formed, and you can understand that in low resistance state, the resistance of the device depends on the nature of the filament or the topography of the filament. So you have this oxide, and the cells are formed at different parts of this oxide depending upon the diameter or the polycrystalline nature, the presence of the bias and the non-uniformity in this oxide will result into the formation of filaments which have different lateral dimensions and which have different thicknesses and so on. And that is responsible for changing the resistance of the low resistance state from one point to another point, and results into non-uniformity of the cell response. When you have filaments, when you have each element consisting of one nanorod or a number of nanorods, a finite number of nanorods, each filament will be formed inside the diameter of the nanorods. So, in present case, we have diameters of around 100 nanometers. If you reduce this diameter further, you have a very small dimension in which the nanorod or the filament can form. And thus, by controlling the diameter of the nanorod, what we are controlling is we are controlling the lateral extent to which this nanorod filament can grow. And this can be one of the methods by which we can improve the uniformity, cell-to-cell uniformity of the device. So now I'll spend these 5 minutes on the fourth example which I took, that is on the solar cell. Solar cell, you know, is based on a PN junction, and when we expose the light, the photogenital carriers are generated, and the role of a solar cell is to to use the electric field formed at the depletion region between the P and N side to separate these electron hole pairs. The efficiency of a solar cell depends on these parameters: absorption coefficient, density of state, band gap, and diffusal. What I wanted to show you was that some of these parameters we can control by controlling the dimension of the nanomaterial. So if we form a solar cell using nanoparticles and nanorods, it is possible to change the band gap of the semiconductor material and hence change the wavelength at which the solar cell will work efficiently. What I want to show you is that if you have one semiconductor, if you have a p-n junction of a single semiconductor, the band gap of the semiconductor is fixed, and you have different energy photons in the solar spectrum. Only this particular photon will be efficiently absorbed. This photon will be transmitted because its energy is less than the band gap energy. This photon will be inefficiently absorbed because part of this energy will be converted to heat energy. What is required in a solar cell is you cannot work efficiently with one band gap solar cell or one junction solar cell. And normally in thin film technology, what people use is they don't use one, so you have to use a large number of solar cell materials, each material consisting of a different semiconductor and hence a different band gap. And so if you have the active layer cell 1, which will absorb one particular type of photons, the other photons will be transmitted through it to cell 2 and cell 3 and so on. But it becomes a very complicated design because one is that the number of photons has to be counted, that each layer should absorb the same number of photons because the current has to match. Current which is produced in cell 1 and cell 2 should be same. The other problem is the interface. When you're forming interface between different semiconductor materials, the interface, there are defects at the interface, there are structural inhomogeneities, the lattice constant of this semiconductor and this semiconductor will be different, that will result into large number of bending bonds and so on, and the design becomes complicated. So what is proposed is that it's possible to use nanorods of semiconductors, and you can change the diameter of the nanorod, and you can change its band gap. So you don't have to change the material, you only have to have the same material, and you can change the diameter of the nanorod, and you can absorb the photon efficiently depending on the diameter. So these are different configurations which people have reported as using nanorods. This is, you have standing nanorods of material A, that's a cadmium telluride for example, and it's covered by another material, a thin film cadmium sulfide. So you have the junction at this point, and you have large number of parallel network of junctions. This is another kind of, this is called a cylindrical solar cell, where you don't have a thin film second material, but you have standing nanorod of material A, and the shell of this rod is material B. So you have two semiconductors joined together like this, or you can have a tandem kind of solar cell. Material A making half of the nanorod, and material B forming second half of the nanorod. So these are different kind of junctions which we have observed, and each one has certain advantages and disadvantages and challenges when one has to fabricate. These are also kind of nanorods people have reported, where the nanorods are not standing, but they are dispersed on the substrate, and you have the junction in this case is parallel. So I would like to show you some very interesting experiments which we did, and one can appreciate that the difficulty in this kind of junction will be how to fabricate it. If you have, let's say you fabricate, you deposited one nanorod, how do you grow nanorod of another material on top of this nanorod? Or you have one nanorod, how do you cover this nanorod with a second material? So we did a very interesting effect. We deposited cadmium sulfide nanorod by a very simple method which is called a hydrothermal method. These are transmission electron microscopic pictures. You can see these are nanorods of 10 nanometer diameter and around 100 to 150 nanometer length. And this is what we did. So if you assume this is a nanorod of cadmium sulfide, we deposited a powder of copper chloride on top of this nanorod, heated them to a certain temperature, and some sort of interdiffusion of cadmium and copper takes place. So what this was a cadmium sulfide nanorod, it gets with copper chloride, and half of this nanorod will get converted to copper sulfide, and cadmium chloride will come on the top, which is water soluble, then we wash these nanorods in water, and what has happened is this cadmium sulfide nanorod has been converted to, we have formed a junction in the nanorod where half of the nanorod is cadmium sulfide of material 1 and half of the nanorod is of material B. So this is basically able to form a heterojunction within a nanorod by using a very simple chemical reaction. You can see that this is one of the cadmium sulfide nanorods where copper chloride powder is deposited, and this is a high resolution transmission electron microscopic picture of one nanorod of cadmium sulfide. You can see it's very high quality, monocrystalline in nature, and this is where you have been able to convert part of that nanorod into material B, copper sulfide, and there is a junction. And this junction we could investigate using a paper of the conducting atomic force microscope. This is a cadmium sulfide nanorod. This is the AFM picture of this. And what we see is this is the IV characteristic. If we put light, we see some photoconductivity due to cadmium sulfide is a photoconducting material. And this is another experiment which we did after forming the junction. And what we see is this is the dark IV characteristic and this is the light IV characteristic. And these are consistent with the energy level, energy band diagram which we formed, which was the platinum tape here is in contact with copper sulfide, and form energy band diagram, this IV characteristic matches with this. And this single nanorod that we found was, it has a preliminary experiment which we did, and it has a efficiency of around 2%. So this, I think I would like to conclude my talk by stating that I took 4 examples. In the first example, where nanoparticle based switchover mirrors, we saw that size-dependent change in the absorption edge and surface activation of hydrogen molecules improve the properties of this material. Radium nanoparticle-based hydrogen sensors, size-dependent shift of radium 4D centroid, nanoparticle gaps, and surface area enhancement improve the properties of the sensor and change the saturation response to a pulse response for hydrogen. Nanorod-based resistive memory devices, confinement of filament formation process along nanorod dimensions, and nanorod solar cells with the size-dependent absorption edge and monocrystalline nature can improve the performance of the solar cell. So these are my students who actually are responsible for doing this work, and these are the supported our work. Thank you very much.